Yeah, like that.
Have your seats, please.
Password for the computer again.
All right, we really need to get going. Please have a seat. Okay, so this next session will start up at one point and end up in a completely different point. But it's still resuscitation, and it's kind of connected. So first out, are we happy with the, yeah? Is Tobias Gauss, a French anesthesiologist working in London at the moment, in hospitally and pre-hospitally. And he will talk to us about cardiac arrest. Yeah.
So, hi, my name is Tobias. It's a great pleasure, and I'm very humbled with you. Doesn't work? Here we go. Is that better? So I'm very happy to and very humbled to share with you some thoughts on intelligent information system, and the case study that we'll try to use is cardiac arrest management. And maybe we can bring up the slides. So my name is Gauss, as the famous mathematician, but I'm actually an artificial and math stupid. I'm a dummy, so to the despise or demise of my math profs in school. My legitimacy to talk about this topic is rather limited, but it stems mainly from the work we're trying to do with a research group in France to set up a artificial intelligence enhanced trauma decision support tool. Just work for the slides. Okay, quick poll. Who has worked with an artificial intelligence enhanced decision support tool in the room? Okay. Who considers himself to be a techie? Okay, a few techies. Who considers himself to be a geek? More geeks here. Okay. Who has some concern about the deployment of artificial intelligence in medicine in general? Okay, so that's half. Who would be happy or very curious to work with an artificial intelligence enhanced decision support tool? So it's a bit, there's a geographical divide here. Okay, so I share some of your concerns and I share also the enthusiasm. So I warn you, until we have the slides up, this will as much an educational talk as a rallying call, okay? Because I think this topic will seize us if we don't seize it as a community, as a medical community and as resuscitationists. So some of the things I present, for those who know a bit of artificial intelligence, and we have the pleasure to have a real expert here with us, many there are other experts, so some of the things I will present are deliberate simplifications to stir up some discussion and to actually, thank you, and I hope we have a lively discussion afterwards, and some are deliberately a bit controversial. So, you see, great minds alike. I have the same slide as Richard, so that's first good point. It's not a buzz, it's a reality. The machines are amongst us, okay? It's not utopia anymore. They're deployed in lawmaking, policymaking, finance, engineering, predict recidivists in criminal offenders. So that's not utopia, it's reality. And want it or not, if you like it or not, we have to face it and we have to learn to deal with it. So let me cite Clemenceau, as we agreed on some concerns, and a big opportunity here. Clemenceau said, war is too important to be left to the generals. Well, I think as a non-techie that AI is too important to be left to the techies, okay? So that's why it would be great that we share some thoughts about this. General thoughts. It will not be a very technical talk, because we have to seize this topic, as I said. If not, it will seize us. Let's agree on what we talk about. We talk about so-called intelligent information systems. That means that with the computational capacities that we have now, it's possible to converge, digest, extract, and process a lot of data and generate probabilities. This can be done with so-called artificial intelligence, proper artificial intelligence. For example, DeepMind, where usually they use neural networks to generate probabilities, so the machines work on their own, as well as an array of complex statistical methods, more like into machine learning, and both of them generate probabilities. And if you merge them into a system where this information is then displayed in a user-friendly, ergonomic way, we could call this an intelligent information system. What is the rationale behind this? I hope you agree that one of the most basic and most important skills that we have as clinicians is to put order into disorder, to identify patterns in disordered information, okay? So, small reference to Ludwig Boltzmann. Are we any good at it? We probably think we are. Who thinks he's a good decision maker? Okay, so, well, who thinks that he makes... I'm terrible at making order in my children's room, for example. The evidence shows that when you look at it, it's so and so. Probably we're 50% of the times right, 50% of the times wrong, for many complex reasons. And one of the main theories that try to explain this is the so-called dual process theory. Stems from cognitive science. So we probably oscillate in the mode of functioning between the gentleman represented on the left, more artistic, heuristic, intuitive, expert-based, and more to the right, gentleman to the right, is logical reasoning, A plus B equals C. And we use this as a cognitive toolbox, yeah? And very often we don't know which tool we actually use. So this makes our decision-making probably inconsistent. The machines, on the contrary, they're supposed to be consistent. They're supposed to be reproducible. They're supposed to have quantified analysis of data, the same data in an understandable way. It's not some black box decision-making. So this provides a great opportunity, let's call it data utopia, artificial intelligence utopia, as well as a big challenge, a dystopia to society and the medical community in general. So let's look at data utopia and use out-of-hospital cardiac arrest management as an example, as a case study. What could this bring to you as a clinician, really, very concretely to your decision-making? Data utopia could be a sort of cardiac arrest cockpit, where a lot of complex data is processed immediately, even complex data that you probably don't dispose of, and you show up on scene, and the machine provides you an immediate ROSC probability, or an immediate, the most likely cause for the cardiac arrest. So this is then displayed in a very ergonomic, user-friendly way, comparable to a cockpit. If you share this information among all the providers in the rescue chain, and you heard about RETS yesterday, this will empower all the providers along the rescue chain. They will be able to talk to each other. They will be able to share information online in real time. And this will empower the decision-making based on probabilistic decision support. And you can have the individual patient data running continuously evolving, and the machine is learning at the same time, and you can have population-based data in the background to back it up and to compare it to a huge amount of data. This is a great anti-fragmentation tool. We know that acute care is fragmented according organizational, institutional, cognitive lines. So if people can share this information in real time, they can better anticipate, better share, provide input, and so this is an anti-fragmentation tool. It's also a great standardization tool, because if we link this to evidence-based guidelines and procedures, then it's much easier to have a interactive cognitive aid that will make us do the basics right. And as Richard said, it's very, very important to first get the basics right. This work is a very interesting work from a colleague from Lyon. They constructed a handheld digital cognitive aid and deployed it to simulated cardiac arrest for trainees. So with a group that had the cognitive aid and one group that did not dispose of the aid, and you see it not only improved their technical performance, as well it also interestingly improved their non-technical performance. If you bring all this together, like decision support, the large amount of information that is automatically extracted and analyzed, this provides a new basis for targeted, individualized medicine. And it's a great benchmarking tool. All the great work that Richard presented, if you have this automatically extracted, put into data warehouses, this is a great way to benchmark your work and to have continuous automated output reports on key performance indicators. So Richard as well mentioned the quality of the chest compressions, which we know has been a confounding variable in the recent randomized controlled trials. If we have automated and analyzed benchmarking of this indicator, it's much easier to control the confounder. We have automatic archives and documentation of our data, reduces the redundancy and improves the quality of the data, and there are no more paper PRFs that are patient record files that are lost, or things that you cannot read or that are not recorded. So it's a great way to archive and document data. And it will help us to analyze complex data that we're currently not able to analyze, like heart rate variability, which is a promising indicator of physiological deterioration. We were not able, we knew about this, there's nothing new, but we just didn't have the computational capacity to analyze it. And now with AI and artificial intelligence, it's possible, and that's a signal that as a clinician, we have difficulty to analyze. This is not utopia, this is reality, this is happening. So this is an example of other startups. It's a startup from Copenhagen that's developing a decision support tool, artificial intelligence enhanced, and they say they have a much better rate to recognize cardiac arrest on the incoming call than the experienced dispatchers. Interestingly, if you look at clinical trials, there are currently no clinical trials registered to look at artificial intelligence deployment out of hospital cardiac arrest management. And there are only 19 publications on PubMed, even with a complex search, and they most of the time deal with ECG analysis or rhythm recognition. So that was our travel through utopia. Some of this is already reality and happening. Let's take our ticket to go to dystopia. You remember this gentleman probably. Are the machines actually better do they perform better? And we're really in the early stage, and people who know this well will say this will come, and the machines will become better. But currently we have to say that they struggle as much with uncertainty and a large variation of data and variables as we do. So the known and unknown unknowns remain a challenge even for the machines. One reason is missing data. Missing data remains a challenge, even from large registry, or in particular from large registries. So there are methods to imputate data, but it remains a challenge, and machines need actually a high level of quality of care of data, and that's called what's data granularity. So the more specific the data and the more detailed, the better you can actually customize your solution to the system where it's deployed. If you develop a system in the US and you deploy it to Europe or vice versa, or to Latin America or Asia, it will probably not work the same way. So you need a high level of data granularity. And this data granularity, a recent example is the deployment of Watson. Watson has been deployed in lots of hospitals, oncological hospitals by IBM in the world without any scientific evaluation. It turns out that if the data become wobbly and shaky, Watson actually struggles as much as the clinicians, and it seems to generate contradicting or conflicting predictions. Why is that? So in a very simplified way, and there's probably a lot to critique about this scheme, it's probably because there's a trade-off between the capacity, the predictive performance of the models, especially of deep learning or neural networks that have a probably higher predictive capacity, but we struggle to understand how they come to the conclusions against machine learning that have maybe a lower predictive performance, but we are much more able to understand them. So there's a trade-off to make. And this is called the black box phenomenon. So there are many examples where the machines come up with very interesting predictions. They actually identify patterns that we haven't seen before, but we struggle to understand how they get there. And interestingly and ironically, the experts call this intuitive pathways. So we have an irony to our dual theory, cognitive theory, and a black box as in the human decision making. One solution could be automatic data extraction. So is that the machines extract and suck in a lot of data from their environment, but you could imagine that they need a lot of data to be enabled to have the same amount of data at their disposal that a clinician has at his disposal, for example in a regional cardiac arrest system, which poses a real challenge to technical compatibility. If you want to enable the machines to the same extent that clinicians are enabled by the vast array of information in their environment, you would have to make all the systems and platforms compatible to each other and be able to talk to each other. So that's possible, and there are already some works undergoing to improve standardization of data formats, but it's nevertheless still challenging. As challenging is probably the cognitive, institutional, and regulatory silos that we have that we live in, to share this data and get access to this data. So from personal experience, I can tell you that it's not so easy as it seems. And this comes with the problem of scale. If you put all this into reality, this is actually quite expensive. And some people estimate the cost of such a system on a regional level, on a regional scale, to be about $500 million. This is equivalent to a new hospital. So there's a real policy change, a real policy choice to make between hiring new health professionals, dying species in our health systems, or to pay for a new information system. Such a system will also be more interdependent, more fragile, and less resilient, as recent NHS cyber attacks have demonstrated. And will become a great and very powerful leverage to ration care and control expenses, which will probably then further the bureaucratization of care. There's a real risk about an increased bureaucratization of care. And this poses a real challenge for our understanding as professionals and of our model of professional autonomy, and creates a conflict between professional autonomy and regulation. So imagine your GMC or your board then sends you a mail in a few years and said, well, in year 2022, you deviated 10 times from the artificial intelligence supported decision making. Why did you do that? Or imagine a team is in the middle of a resuscitation and the machine says, you should not thrombolyze the patient, or you should thrombolyze the patient. You're convinced of the contrary, but the team knows what the machine suggested and challenges your legitimacy. There's also a risk of cognitive de-skilling. Think about GPS. So it's not a joke. There have been data, or there's some studies out there. People are not able to read a map anymore because they're so used to use GPS. So we learn by exposure and we learn by reinforcement cycles. So if we always have now this tool available, probably we get de-skilled, and this will much more apply maybe to future generations who will never learn without any artificial intelligence decision support. And then there's the business model. Okay, so we won't have time to dig into this, but I think there's potential conflicts of interest, and the forces driving and pushing for AI deployment in medicine and in the society is one of the main problems, and maybe we have time to talk about this in the discussion. So you see, lots of potential for opportunity. It's really, it can be a game changer, but it can also be a game changer to take us to dystopia. So what can we do? what can you do? I think we should first of all, and I hope this will generate some discussion and controversy, we should take ownership of this topic, all of us. We need to become, at least, we don't need to become experts, but we need to become knowledgeable. That means we have to start the dialogue in our institutions and ask for AI committees. It's already happening. It's not the future. It's happening right now. So we need AI committees. We need ethical committees. We need to develop this topic and seize it. One example is regulation. Not very sexy right now, but we need to lobby for regulation. Very old-style regulation, I think, because they will be like medical devices. They are like drugs. They are like prostheses. So they require very old-fashioned regulation. And this regulation needs to be based on sound and rigorous scientific evaluation. And this probably we have to develop new methodology to allow us to assess the deployment of AI in medicine, and also assess what impact deployment of AI has on our professional behavior and of us as a community. Here we can learn maybe from the aviation industry and their sector approach. We have to accept finally that we are a medico-economic sector and we have to work together as a sector. And to become a sector, I think we need to think about our relationship, our love-hate relationship to innovation. And I all invite you to read this great paper. It's only 5 pages long, from René Alberti and Mary Dixon Woods. I have a handout that I can send to you with all the literature and bibliography and things to read, and summarizes my presentation. Is there a possibility, if we manage to not have dystopia, to prevent dystopia, to actually go to utopia? And I think there is. And I think the way is to embrace and develop our human factor capacity as a clinician and within our institutions. If we develop our human factor capacity and the human factor approach, we can counterbalance or balance maybe some of the effects of AI deployment. And we bring this together with AI. This will actually be able maybe to unload our cognitive buckets, to let the machines do what we don't do well, to do the redundant stuff, the stuff that bore us, the stuff where we're not good at. And when we unload our cognitive buckets, we have more space and time to become, again, great team players, great clinicians, and to have a proper synergy between human factor and AI to have an enhanced human factor approach. So I hope that I stirred some questions, and there are probably some simplifications in the presentation. But I'm looking forward to the discussion, and thank you for your attention.
Thank you, Tobias. Great talk. And you see, these themes are interconnected. If we don't involve in you know, the algorithms and the making of interpretation systems, we're in deep shit. So we'll have more on this now with Mathieu Komorowski, a French anesthesiologist also working in London right now. And he will tell us about his PhD project, which is artificial intelligence in sepsis.
Thank you. Okay, can you guys hear me okay? Is it too loud? Okay. Well, I think, Tobias, that was really great introduction, really great way to bring the topic. And you talked about many other layers, many extra layers that I'm not even gonna touch upon. This is an example of I think the state of the art in artificial intelligence in medicine, what we're currently capable of doing, and you'll see that from some of the slides I will present that we're quite safe probably for a while. And the idea of all this approach is really not to replace doctors with machines. The idea is to reduce the uncertainty around some of the decisions that we make, and I'll hope to try to convince you of this. So Great to be back in Zermatt. Last time I was here was last summer. I ran here from Chamonix, so it took me about 8 days, 250 kilometers. And arriving here was really an emotional thing, so I have a special connection to this place. It's really, really nice to be back here. I thought I would start by telling you a little bit about what I do and see how different it is from what some of you guys do. Okay, so what did you think of yesterday's talks? Yesterday's presentations? Yeah, I agree with you. It was horrible. It was gruesome. It was disgusting, right? We started by the video of this poor guy bleeding to death in his mouth, right? Then we heard Levitine telling us how his ships have dead bodies around the world. I don't know why. So they're not half dead. They're completely dead, but it's only half of them, right? Then we had Ducanto, watching Ducanto playing with fake puke. Then in the afternoon it was some more gruesome pictures of war zones, right? Then it went completely what the fuck. We learned that we could cool down cardiac arrests with French fries. You remember that? Then we got to play ourselves with fake vomit. And la cerise sur le gâteau, the icing on the cake, we got to intubate a teddy bear while drinking beer. All right? It was an interesting day. So this is very different from my day-to-day basis. I do big data analytics in ICU. I do machine learning. This was my office at MIT, and you see there's no blood, there's no vomit, there's no dead people, right? Although I do work as an intensive care doctor, but my patients behave. They don't bleed, they don't vomit, they don't die. Okay, it's clean. Okay, let's talk about sepsis. Is it working? Sepsis, good. I don't have to convince you that it's a major healthcare challenge. It could be infectious disease. It could be the second or the third leading cause of death worldwide, right? And it's a major source of healthcare expenditures. Treating sepsis, if we want, we can really broil it down to 3 major points. First, we need to control the source of infection, and this we know how to do this. We know we need to act quickly, get the abscess drained, get the antibiotics in, and so on. So that's fine. Correcting hypovolemia in vasoplasia, I think, is really the pain point, the difficulty in dealing with sepsis. So this is what I'm focusing on. The third aspect is about treating secondary complications once they occur. So replacing organ failures, doing dialysis, treating clotting disorders, and so on. So more or less, we have a fair idea of how to do this. So hypovolemia in vasoplasia is the key problem. You've probably seen this curve before. There's a U-shaped relationship between the amount of fluid you're going to give to a patient, so that's the x-axis, and the onset, the occurrence of complications. If the patient is underfilled or overfilled, you're going to run into problems. So there's a sweet spot somewhere. Do I have a laser? Yeah. There's a sweet spot somewhere in the middle where the tissue perfusion is optimal, right? But there's lots of problems. We don't know where this sweet spot is. It's different in every patient, and also it's very dynamic. It changes all the time. So lots of unanswered questions about how do we correct hypovolemia? How do we correct vasoplasia? How do we measure? How do we even measure it? How do we define it? What is the correct volemia we should aim for? How much fluid do we give to patients during initial resuscitation, during and afterwards? When do we start vasopressors? What is the right balance between intravenous fluid and vasopressors? What parameters should we be targeting? What do we work with? Mean arterial pressure, urine output, lactate, fluid responsiveness. Why do we correct fluid responsiveness? Why? There are reasons to think that this is the right thing to do, but maybe we're wrong, right? I'm fluid responsive now. Do I need fluids? I don't know. Probably not. I'm not septic, but you get the point. There is more and more evidence coming in that maybe we should be more restrictive with fluids. Here on the left, you see, so it's a retrospective study looking at a cohort of septic patients. It's showing you the accumulated fluid balance day after day in sepsis, and the patients who achieve a neutral fluid balance early, by day 4, day 5, they survive more than those who don't. So having a positive fluid balance is bad, at least after the initial phase of sepsis. Figure on the right showing you the survival or the mortality of patients depending on how long we waited before starting vasopressors in septic shock. And again, there seemed to be some evidence that starting early is probably beneficial, maybe because some of those patients get less fluid, maybe. What are we left with at the moment in terms of guidelines and tools to treat our patients, because there's patients coming in and they need to be treated. So until recently we had the EGDT, and now we think that it's either useless or even potentially harmful. This was the JAMA paper recently last year. So we do have the Surviving Sepsis campaign, and it's a great tool, but there's no real-time decision support system that would allow us to tailor the treatment at the patient level and to deliver what we call precision medicine. So my approach, and I think it fits nicely with some of the things we've heard before from Tobias, is to use machine learning. So machine learning is a type of, it's a synonymous of artificial intelligence, and it simply means learning from the data. There's lots of overlap with biostatistics. There's 3 pillars in machine learning. We can do supervised learning, unsupervised, or reinforcement learning. In supervised learning, it's all your usual mortality prediction models and so on. It's about learning the relationship between some input data and some output data. So if you do regression, if you do classification, you do supervised learning. Unsupervised learning is more about learning what is the structure in a data set. Are there clusters? Are there groups of patients that would be homogeneous? Can we simplify an information by reducing the number of dimensions in a data set while keeping as much information as possible? So that's unsupervised learning. The third pillar is reinforcement learning. This is what I do. And it's about learning an optimal strategy. So you use some of the other tools in order to do reinforcement learning. This is what we're going to focus on. I'm going to take a step back and try to give you some intuition behind reinforcement learning, because it's not that straightforward. Think about what do we do when we make decisions about a patient. So we're in the ED. There's a new patient coming in. We're going to collect data about this patient to get some idea about what's happening. And then we'll compare this to our theoretical medical knowledge, what we've learned at medical school or during conferences, reading papers and so on. And then we're going to compare this to a third aspect, which is our clinical experience, the sum of all the previous patients that we've seen. And integrating all of this, we're going to make decisions. Do you agree? Problem is, this is very, very suboptimal. This is very biased. We have so many cognitive biases when we make those decisions. Very often, we don't have any physiological or pathological model to explain what's happening to a patient. Sometimes we don't have the theoretical knowledge. I don't know everything about medicine. I'm far from knowing everything in medicine. Sometimes you've seen previous cases that were very similar, but you just forgot that you've seen those patients. Sometimes it's so rare that you have no idea what's happening. Often we get the diagnosis wrong. How many patients with, I don't know, COPD exacerbation end up on diuretics? And practice variations is huge. It's a huge problem in my opinion. I don't make the same decisions at 2 p.m. and 2 a.m. I don't make the same decisions as the other consultant next to me on the same unit treating the same patient. Practice variation is huge, and some of those decisions are good. Some of them are not optimal, and the idea behind those approaches is to try to reduce these variations and get the decisions right more often than we currently do. So if we were to think outside the box and think about what would be the perfect medical system, there's a few ways to define this. If we had complete knowledge of all human physiology, whole human diseases, all possible human treatments, all the effects of the treatments, and knowing what would be the most optimal one, of course that would be the perfect medical system. You agree that it's completely impossible. An alternative maybe would be to have a permanent and unbiased knowledge of a very, very vast similar number of patients that would be very close to the patient in front of you. If at the same time you knew exactly what treatment they received and what was their outcome, maybe that would give you some idea of what to do. And you can try to picture it in your head by thinking of a cloud of data points, a cloud of patients that look very similar to a new patient just coming in and who's in front of you, if you knew exactly what all those people were treated with and what happened to them, maybe that would give you some idea of what you should be doing with your new patient. Okay, so this is a bit of intuition behind reinforcement learning. We're going to group patients by similarity and look at what treatment they received and what was their trajectory as a consequence of those decisions, and hopefully try to optimize those what we call policies, the treatment strategies. So reinforcement learning, as I said, it's about learning an optimal strategy. I'm going to give you a very quick example here. There's a couple of items you need to define in order to run reinforcement learning algorithms. So you need an environment. So here, the environment is a maze. The agent that's going to evolve in this environment is a rat. And the purpose of the rat is to reach the cheese as often as possible. That's the reward that the agent is going to be seeking. The agent wants to maximize the reward as often as possible by making the right decision in every state of the environment. And at the same time, the agent wants to avoid the penalty, here the penalty of being electrocuted. So in reinforcement learning, we want to learn the optimal strategy, what actions need to be taken in every state of the system in order to reach reward as often as possible. And if you think about it, that's not completely different, at least in theory, from what we do in a hospital, right? We have a patient, the patient can be in different clinical states. What we want is to send the patient home rather than to the cemetery. And we need to make decisions depending on the current state of the patient. This is the intuition behind reinforcement learning. We can formulate medical decision as a reinforcement learning problem. Here we have a physician acting on the patient. The physician acts on the patient by intervening, giving them drugs, sending them to theaters, turning on the dialysis machine, and so on. In my research, the action is intravenous fluids and vasopressors. The patient is going to switch states, is going to move into more better or worse states as a consequence of the action, and also as a consequence just the evolution of the disease. If the new state is better than the previous state, the agent, so the physician, is going to get a reward, and this is going to reinforce its behavior. This is why it's called reinforcement learning. Good actions lead to are being reinforced through the process of reward. So if we had a system like this, we could ask two questions. How good is the policy of the physicians? How good are we at making decisions? And of course, can we identify an optimal policy? Can we identify what would be the best decisions in order to maximize survival? That's what we care about. Most of this actually was in some of your slides, Tobias. So most of the advances that we've seen in the previous years in AI were related to some extent to reinforcement learning, including those Atari games in 2015. But why can we just not do this for medicine? Why is the literature not flooded with papers like this on sepsis and everything else? So there's a couple of reasons. In medicine, we only have a limited amount of training data. They used millions and millions of virtual hours of video games in order to train the models. In medicine, the environment is not fully specified. Here, at any point in time, you have all the information you need on the screen in order to make the best decision. We don't have this for medicine. We don't know what's happening. We're only looking through the keyhole of the vital signs, the lab values. We don't know the whole physiology. We don't have the full picture. In medicine, it's impossible to learn by trial and error. This is what they do in computer science papers. So it's impossible to connect a patient with sepsis to a machine, let the machine play, try different random doses at the beginning and see what happens. Completely impossible. And on a similar line, we don't have a simulator to test the suggested strategies. Much harder. So in my research, I've used two data sets from the US. They contain data that was routinely collected for patient care. So I do secondary analysis of routinely collected data. The total number of patients in those data sets is nearly 100,000 patients coming from over 130 different ICUs in the US, included adult patients with sepsis, about 48 parameters, 48 features for each patient. So this is demographics, vital signs, lab values, fluid intake, current vasopressors, fluid balance, outcome, and so on. And 72 hours of data per patient. So if you put all of this together, it means we have over 680 years of data. So imagine if you had the possibility to remember 680 years worth of patients with sepsis in your head, know exactly what treatment they received at any second, and what was their outcome. This would be a tremendous amount of information if you were able to process this. And this is what these algorithms do. I'm going to go quickly here, but basically what the model I use is a Markov decision process. So I use the training data to define the elements of a model that allows to implement reinforcement learning algorithms. Okay. Then there's two big algorithms that are used. One is what we call policy evaluation. So we evaluate the policy of doctors. We run the data through an algorithm that tells you this action in this particular state is worth 50 points because most patients survived. This action is worth minus 80 because most patients who received this dose of treatment in this particular state, they died. We evaluate an existing policy, and then we estimated an optimal policy, what would be the best decisions to be made in every state of the system. And this was then tested on external data sets. Some results. So again, some really clean slides, no blood here. It's all generated on a computer. But what we see here is this is when we evaluate the policy of doctors. On the x-axis is the return. So it can go from minus 100 to plus 100. This is basically a grade, a mark you give to any decisions. And what you see is the model is well calibrated because there's a homogeneous relationship between the return, so the value of the actions, and patient mortality. The actions that are very low return are associated with extremely high patient mortality, and the other way around at the other end of the figure. So we were able to learn this relationship. We're able to quantify the value of doctors' policy. And this is very similar, showing you here the average return per patient versus outcome. So the survivors have a much higher return on average. The value of actions that were taken in patients who survived is much higher than the value of actions that was taken in patients who didn't survive. Okay? How optimal do you need to be? So we know now we have a grade. We have a mark for any possible action in 680 years of patient data. So we can start playing with this. For example, do you have to be extremely optimal? Does it matter if you take even the second most optimal action in a state? And the answer is probably yes. So if 100% of the time you take the most optimal action, the mortality is about 8%. If you take even the second best action, 11%. If you take the third best action, 14% mortality. So there is an increase, and the differences are significant because obviously the number of data points is very high. So being optimal does matter. Again, this is observational, retrospective. Now we have evaluated an optimal policy, meaning we ran the algorithms and something came out. The system tells us, oh, for this patient, you should be giving 0.1 of NORAD instead of 0, and you should stop the fluids because that doesn't seem to be the most optimal decision. So we can compare the policy of doctors here on the left and the optimal policy on the right. What I'm showing you is the distribution of the doses of drugs. So let me try to explain the figure. On this axis is the doses of vasopressors. So it's norepinephrine equivalent, mics per kilo per minute. Okay, so all these patients were receiving no vasopressors, and on the other axis is the dose of intravenous fluids. It's in milliliters per 4 hours. That's just a convention in the model. So you see the doctors, they gave vasopressors to only about 10 or 15% of the patients. Most patients were not on vasopressors, and many patients were receiving a fair amount of intravenous fluids here. Okay, if we compare this to the optimal policy here, you see about 70% of the patient should be on vasopressors according to the system, and the doses of intravenous fluids should be reduced significantly from what the doctors are doing. So this is interesting information if we think back about the papers that we've seen about fluid balance, about initiating vasopressors earlier, and so on. So so far we don't have any justification about why the system is telling us this, but I'll come to this. how do we know that the suggested doses are optimal? This is a key problem, right? Where's the evidence? And again, it's all retrospective, and it's impossible to know the outcome of an action that was not taken, right? Because it's retrospective. So what I've done is I looked at the difference between the dose given and the dose recommended in the patients in the test sets. If this difference is 0, it means that the patients in the past received the optimal dose. Does that make sense? Looked at the difference. So this is what I plot here. On the x-axis is the difference, and then you look at patient mortality. So it means the further away you are from the central bin, where close to 0, the further away you are, the higher the difference between the doctors and the optimal policy. And what you see is the mortality gets higher the further away you are from the central bin. It means that, so intravenous fluids on the left, vasopressors on the right. It means that, roughly said, the more the doctors were wrong, the more the patients died. So this gives us some indication about maybe the value of what the system is doing. We can try to estimate the mortality with optimal action. This is really preliminary work, and different approaches give you different numbers, but at least the expected mortality in this approach, for example, without going into detail, the actual mortality is about 18% in the test set. The predicted hospital mortality with optimal action would be 10%. So this is huge. This is probably over-optimistic. And as I said, you get different numbers depending on your assumptions in the model. But even if we could achieve only a few percent reduction in mortality, it would be tens and tens of thousands of lives saved, maybe more. So some potential. I think this is my last slide, so we'll be right on time. Tobias talked about the interpretability of those models. And the black box problem. So far, all I said is you feed patients' data in the system, and it's going to tell you, oh, that your new patient should be getting X, Y dose of vasopressors and intravenous fluids. Why does it do this? So we can try to open the hood and see what's happening inside, and why the system is making those recommendations. So in this particular analysis, we looked at what features were the most important for the doctor on the left, for the optimal policy on the right, when recommending to start vasopressors or intravenous fluids. And what you see, so here on the left, you see doctors, when they decide to put a patient on vasopressors, what do they rely on? The SOFA, so severity scores, current fluid input, blood pressure, Glasgow, whatever, accumulated fluid balance, and so on, renal function. Is the patient on mechanical ventilation, and so on. These are the most important features. They are clinically meaningful, right? This makes sense to us. You wouldn't decide to put a patient on vasopressors based on the patient's grandma's age, right? Or I don't know, the patient's INR, or some other features that would not be clinically meaningful. This makes sense. If we look at the optimal policy, so the scale is different. I'm sorry, it's a bad figure, but it doesn't matter, the ranking matters. What you see is, again, clinically meaningful parameters: the blood pressure, fluid intake, severity, urine output, cumulated fluid balance. Everything that's at the top of this ranking, all the features that do matter to the system, are again clinically meaningful. It doesn't seem to be making random decisions. So I hope you agree with me that the current way we treat sepsis is suboptimal. There is so much randomness. You wouldn't believe how much variability there is in the data for two patients that look exactly similar, exactly the same. It's actually incredible. Using reinforcement learning, maybe one day we could develop decision support system that would reduce this uncertainty, reduce this randomness in our practices. And I didn't say it, but this is a very flexible framework. We could apply this to potentially any other clinical question: mechanical ventilation, sedation, glucose control, antibiotics, you name it. As long as you have the data, as long as you're able to model a disease process, this could work. Thank you.
Okay, great. Thank you, Mathieu. A really interesting work and great presentation. Next up is Jakob Stensballe, which is who is a